Okay, welcome to this video. Today we're going to focus on graphing polynomials. And we kind of look at this at the end of the chapter because it's kind of like a visual compilation of everything else we learned this unit and kind of really bring it together and really trying to understand the different pieces and how they all relate in a graph. So here are the focus points, the objectives that we're going to look at in this lesson. One is, can we make an overall graph of a polynomial and understand the different pieces? And those pieces are end behavior, both to the left and the right, and we'll talk about that. Looking at turning points, when the graph actually changes direction, location of them, and the number of them. And the last thing is, can we, find specific points on the graph, intercepts, and also different input outputs through evaluation, synthetic division. So those are the topics that we're going to look at. Now, in order to fully understand this, we must first look at disco music. So let's take a look and see if we can find some math in this. Perfect example of showing you that math is everywhere, even in 70s disco music. So let's take a look to see how that's going to help us with end behaviors of polynomials. End behaviors of polynomials talks about when you plug in large x values to the right, as you approach infinity, and to the left, negative infinity. As these inputs increase and decrease, what happens to the graph? Well, let's first take a look at an example of something that we know. F of x is equal to, let's say, y equals mx plus 3. So I want to say 2x plus 1. I'm just going to make up a function there. So if we were to graph it and sketch it, it's going to look something like that. So it's a linear function. No big deal. Now notice the end behavior. As inputs are plugged in positive, the outputs are also positive and they increase going in this direction. Okay. The same with negatives. As you plug in negative inputs, the outputs are also negative and they go in the opposite direction. Well, as we're going to find out, when we get to functions that look like this, where we have degrees of also other odd exponents, for instance, x cubed, we're going to have the same pattern. Because notice, x to the first power, that's what a linear function is. It's an odd power. So a graph of this nature is going to look like this. It's going to come down and kind of change through there. But notice, as we approach, it doesn't actually curl in. It goes out there. As it approaches infinity to the right and negative infinity to the left, it has the same behavior. It goes up to the right and down to the left. Notice John Travolta's position in his dance move. And we can see the hands going in opposite direction. So we like to refer to as polynomials with an odd degree go in opposite directions like John Travolta. Now, what happens if we introduce a negative into this equation, like negative x cubed? Well, the only thing that changes is the graph gets flipped over and goes in the opposite direction. And we can see that right here. So notice, negative John Travolta and obviously positive John Travolta. Now, how's that different than even behavior? Well, the major even graph and function that we looked at thus far is x squared. And what do you know about x squared? Well, it's a simple parabola. And notice when you square a positive input or a negative input, they both result in a positive output. Okay, so as we approach values to the right and values to the left, they go in the same direction. And the moment that we introduce a negative into the equation, the only thing that changes is the outputs now become negative, but they still go in the same direction. So we could see this in YMCA, the most famous dance move of all. So notice, hands go in the same direction, and if we have a negative YMCA, then simply the outputs go upside down. And we can see that here, part of their dance as well. So again, I just like to use it as a nice way to relate dance to how it can remind us about different behavior in mathematics, okay? And it goes for any degree, x to the 4th power, x to 6th power. So just to show you a quick example, you're going to see graphs that look very similar to this. So you might have a graph that comes down and changes through the middle, but the end behaviors still match and go in the same direction. And we'll talk about what this means here later in the lesson and throughout our practice. Now let's go ahead and take a look at this middle section. What is happening here? We call those turning points. Turning points are where the actual direction of the graph changes. Okay, so let's just draw a couple examples. We may see for instance, x to the 4th power function, and it may look very simple like this simple up and down. We might see another version of it where we have plus 3x to the cubed and on we go, other terms after x to the 4th, and it might look like this. It might actually come down, go up, come down again, and back up again. What we call these are turning points. Let me highlight them. It's where we actually change direction. So notice the graph goes down, gets to the bottom, and changes direction, goes back up. And notice it gets up here and changes, goes down again, and back up one more time. So we call these local minimums and maximums. Okay, and we can use the calculator to identify those. But the important thing to here is the number of turning points. So let's say this is x to the 4th power. Notice we have 3 turning points. So what we do is we take that 4, subtract 1 away from it, and we get 3. So if this was x to the nth power, we'd simply say n minus 1 tells us the number of turning points. Okay, so number of turning points. I'll just abbreviate there. Now that's the maximum number. Sometimes notice in the red function we had just 1 turning point. But again, 1 is less than 3. So 3 is the maximum number of turning points. If we had something of, let's say, x to the 5th power, I'm just going to kind of mix one up here. So I'm going to go down, up, and then, and let's say it was 5th power. That means that we have 5 minus 1 up to 4 turning points. And notice here we see 2. And as long as 2 is less than 4, we're okay. Now the one thing is if we have, let's say, x to the 4th power, and we can clearly see that we have 4 solutions. And again, solutions are x-intercepts. 1, 2, 3, 4. Then for sure, you're going to have 3 turning points. So there's our 4 solutions, and let me identify our 3 turning points. 1, 2, 3. So notice the number of turning points is always 1 less the number of solutions, never more than that. And we can see examples of less than that. Okay, so this is kind of highlighting different changes in the graph that we're going to see in polynomials. We're going to finish this lesson with 2 examples, one showing odd degree function and one showing even degree function. And again, we're going to kind of go back to those objectives: end behavior, solutions, x-intercepts, y-intercepts, different points in the graph, and then also kind of identifying those turning points. So let's take a look and see what we know about this graph so far. Looking at what we can see here, we see, for instance, cubic, so that means odd degree, which we know is John Travolta. End behavior in opposite directions. And being that it's negative, a leading coefficient negative, that means we go in opposite directions here. Okay, so instead of going up to the first quadrant, we'll go up there. The other thing is, let's go ahead and try to find solutions. Now, let's say, notice I have the calculator over to the right, but let's say we can't use the calculator. I can go ahead and factor that. So I'm going to use grouping. And again, I can factor out the front, factor out the back. So when I do this, I'm going to take out a negative 1. And I take also out of x squared, and I'm left with x minus 1. And in the back, I can take it out of 3, and I do the same thing. Okay. Now notice, when I group this, we have a negative x squared plus 3. That negative is the leading coefficient, so we want to take that out as well. So this is what it looks like right now. We don't want to lead with a negative, so I want to put the negative out front. And we've seen that before in our factoring, and it looks something like this. So from here, if I was to solve that, and these are all set equal to 0, if I was to solve that, we know we're going to get solutions of 1, square root of 3, and negative square root of 3. Okay. And again, these are all ordered pairs, and these are solutions. And we could see that from factoring. So let's go ahead and get those on the graph. And those exist at 1, and then roughly 1.7-ish, and negative 1.7-ish. Okay. Now, the number of turning points could be up to 2, 1 less than a degree. So let's go ahead and turn on the calculator and see what our, what we've kind of concluded and see if it's accurate. So let's go ahead and graph this here. And notice we have end behaviors that go up and down. We have 2 turning points. And notice it looks like it goes through those points. But notice, let's say I didn't factor it. I just looked at the graph and said, all right, it looks like it goes through -2. I'm going to use synthetic division to test that. And we talked about this in our synthetic division lesson. So synthetic division, again, is -1, 1, 3, -3. There's my coefficients. I'm going to synthetically divide -2. Now watch what happens here. If I go through this here, we get an output of 3. So this is, notice, not a solution because my remainder is not 0. But it is an ordered pair. So it's a very effective way to get specific points on the graph. So we can use that. So let's put that on the graph, -2, 3. So notice that solution, which is the square root of 3 being found from factoring, is close to -2, but not there. So we use synthetic division to test that. Okay. Now let's go ahead and test this point, 1, 0. Let's see if that was actually the case. So I'm going to use my same coefficients again. I'm going to test 1. And notice this time we get a solution of 0. So when I see that, there's my output, there's my input, and we can see that right there. So a great example how we can use synthetic division to test those solutions. Now, another good point to find on the graph is simply your y-intercept. We take 0, plug it in to the equation. And again, we don't like to use the word plug in. We want to evaluate, and then we can also use synthetic division to do that. Now, let's just imagine if we put a 0 in front of synthetic division, all of those values drop out, and then what's left on the end? Simple -3. So we can see that in the graph too. Okay. So again, we're either evaluating or using synthetic division for here. And then again, our last step is just kind of connect the dots here. So end behavior starts up here, goes down, back up, and down. Now the last thing we want to pull out of this graph is we want to find the actual height of this turning point. And we call that a local maximum because the maximum is way over here. The range doesn't have a limit. But what's the localized maximum? So we're going to use our calculator to identify that. So we're going to go to calculate maximum. And we just do it just like we did with quadratics. Get to the left, and we get to the left, so we kind of define the domain that's looking in. And it should give us a value right here. So we're getting a value of 1.4 and 0.4. And let me get this last point in. I forgot to write this down, so let me include that. But then we're going to find that local max at 1.4 and 0.4 here. So another way to get some valuable information. Okay. Let's take a look at one more example, which is x to the 4th power. So here we have an even value. Notice the leading coefficient, 1, is positive. So we know that our end behavior is going to go up in the same direction here. Okay. Now let's go ahead and jump right to the graph. Let's say you looked at this and you're like, I'm not sure how to factor it, or there's too many terms in it. What we can do is use the calculator to get us started. So I'm going to go to y equals. I'm going to turn this one off, and I'm going to turn this one on, which is this function we can see. And let's take a look at it. Notice we can see end behaviors in the same direction. Notice the number of turning points, 3. And notice we can see all 4 solutions, which means all 4 solutions are real, no imaginary solutions in this case. And let's go ahead and test them. So it looks like -2, 1, 1, and +2. So I'm going to try those points out. I'm going to try those endpoints out. So we have -2, -1, 1, and 2. And those are the inputs that I'm going to evaluate using synthetic division. So let's go ahead and try that out. Now, let's go try it -2 first. Now notice when I synthetically divide this, I need to do 1. There's no x cubed, and there's no x to the 1st power. So it's going to look like that, obviously. We're going to try -2 first, and we're just going to kind of fly through this because we're doing a pretty good job at synthetic division. And notice we get a value of 1. Okay, so we're going to get that point on the graph, -2, 1. Now I'm going to tell you right now, this is for the sake of time, this is symmetrical, so we can see that at 1. But notice it's not a solution. So let's go ahead and try this value. So I'm going to try -1 this time. Again, I'm going to grab the same coefficients from the original function. And this time here, we're going to see what we get. Actually, this is -3, and that becomes +3. Sorry about that. And we get a 0 here. And notice that is a solution. So we're going to identify that and put it here. And it's symmetrical. That doesn't always happen, but just for the sake of the video, I'm going to let you know if we did synthetically divide those two sides, we would get the same values. So notice that is a solution and a solution, and we got this point. So notice we got a point right next to it. So how do we identify those two other solutions? Well, let's take a look. If we look at the remainder of our item here, let's go ahead and take out this other solution, this other 0 of 1. So I'm going to take 1, and notice I'm going to take it out of the remainder here, the remaining polynomial that we factored out. So let's go ahead and do this here. And notice that goes to 0. Now, let's take a look at what's left. So those are the two zeros, the two factors that we took down. And notice we have this chunk left over. This is the remainder, x to the 0 power, x to the first power, x to the second power. So this is really x squared minus 3. That's what's left. So if we want to solve that portion, we can simply set it equal to 0 and solve. And notice that's what we're going to get. And we've been doing a lot of practice on that. So notice that is that, 1.7-ish, really close to 2. So we can kind of get that on the graph now. And if we want to write it as ordered pairs, it's going to look like this. Square root of 3, comma 0. Negative square root of 3, comma 0. So notice all the information of specific points we're able to get here. And the last specific point, do it in a different color, is 0, comma 3, that y-intercept. And we can get that value on here as well. So again, if I was to draw in, it's going to look like this. Okay. Now again, if we wanted to find those localized minimums, we could use our calculator once again to identify those. I just kind of estimated them for right now. But notice that we used synthetic division, found specific points, we looked at end behaviors, the number of turning points. These are all things that help us create polynomial graphs. So to wrap up this lesson, notice, looking back at the objectives, we can use multiple bits of information we learned about polynomials and get it all together in one graph. And those again include the general shape of the graph, which includes end behavior, looking at, opposite direction, same direction, how it relates to our examples that we used in Disco. And then turning points, be able to find them, identify them, number of. And lastly, can we use evaluation or synthetic division to find those specific points and locate those on the graph as well. Again, I hope you enjoyed the lesson, and we'll follow up with more practice in class.